I'm lying in bed at 8 sometimes.
And then I was just not reading regardless.
Yeah, you people lies. I read. Says the guy who hasn't handed in like 12 physics.
Hey, that's the balance.
He's late.
Yeah, but it's not those no wait times.
Yeah, no.
You're gonna hate yourself come like a month from now. You're just there for like 3 straight days.
Literally the first semester, we've already managed to fall this far.
I'll try and get like 3 done.
Yeah, we both know that's not happening. This last weekend, when
Pardon?
4 of us met up to do our work and stuff.
There sure is.
They're now and then like,
But we're talking about foundations. Oh my goodness.
It was a stretch.
Foundations.
He's basically, well, he's fresh out
I
of
should have
school,
stayed
right?
in
So he's like
bed.
we were in high school, like, he has-
Are you guys ready for trig or what?
We're still talking about radiation.
I think you guys have done, like, so you guys are taking physics, yeah? So pretty comfortable with trig, radians? No radians? Okay, so we're going to talk about radians today. But from here on out, we're doing trig, sine, cosine, tangent, angles. Nice.
You can just change your function or something like that. Cheers.
Hey, Jared.
Wait, is it Jared?
Busted. No, hey, Jared, can you turn your microphone off? Anyways. Maybe he heard me, I don't know.
Oh, yeah.
All right, so trig here on out. I know, hard to focus. We're not gonna be changing our mode yet, but when we do, we'll talk about it. Because I haven't looked at how to do it. I'm sure it's on here somewhere. Welcome. Oh, I've lost count. Yeah. That's really good. Yeah. Well, I was alone in here for a long time. I'm like setting up. I'm like, I guess I could just take it down if no one shows up. I don't know.
Show up every day.
All right, so section 10.1. So like I said, we're gonna just start trig today, and then we're doing trig for the rest of the term, which isn't actually that long, right? Start freaking out now. I know, right? Yeah. Start the freak out. Okay, so 10.1 is the radian measure of angles. I guess I should capitalize radian. Okay. So we're just going to talk about what is the radian, how does it behave, that kind of thing. And so I don't know if you took maybe math 12. I think it's in math 12. I used to have a little sticker that said, remember radian/degree mode on my calculator, right? Because we're always changing back and forth. But so now we're going to kind of open up the possibility of working in radians. Radians are nice because they're kind of pure, whereas degrees have that kind of unit, right? And so, so radians are preferred in some applications. So we'll start with a little bit of review, right? We've seen angles measured in degrees. We have seen angles measured in degrees. And we know we know things like if I draw this, well, that's 90 degrees, right? So we're familiar with these in degrees. If I draw something like this, right, 180 degrees, and then if I draw something like this, we're at 360, right? So we're familiar with these, we're comfortable with these. And so we're going to talk a little bit about terminology, right? Just so we have kind of the basics, right? So some terminology to recall. If you're drawing an angle, right, then I'll be talking about the initial side. The initial side is kind of where the angle starts. So if I'm using arrows to draw the angle, then it's the start of that arrow, right? That's your initial side. Yeah. It's possible to have an angle going this way, right? Each of those are 180 degrees, but one's going the opposite way, right? And so we've got the initial side, and then we've got the terminal side. Oops. The terminal side. We might hit 50%, guys. We just might. And I'm willing to round up.
On the test.
No, for attendance. Yeah. Yeah. If we're hitting 50% on the test, yeah, I'm willing to round up.
Everyone has this.
Yeah. And so what we said was, okay, so we're gonna have an initial side and a terminal side, right, where it ends. And so two angles are coterminal if they end up at the same terminal side, right? And so you can go around and around and around, but as long as you end up at the same terminal side, they're coterminal. So two angles are coterminal if they have the same terminal side. Right, so for instance, right, I drew the 180, right, 180 going counterclockwise was the first one, right, ended at the, well, at the negative x-axis, right, if we're thinking about it in terms of x and y axes, right, but then also we could go clockwise 180 degrees and they would end up at the same terminal angle, right, or terminal side, sorry, and so they're coterminal, right? Or you can just loop around one rotation. So as a rule, angles, I'll say kind of quote unquote moving, right? So if they're moving in the counterclockwise direction, they're going to be positive. And then if they're moving clockwise, they're going to be negative, right? It's just to indicate which way they're going. So angles moving, right? So from the initial side to the terminal side, so angles moving counterclockwise will be considered positive, while angles I'm just waiting for the time that I write angel instead of angle. It's probably going to happen. While angles moving clockwise will be negative. I didn't get a chance to talk to Frank about what type or like what kind of trig you guys have gotten into already.
We've literally just did sine, cosine, like the
Little-
simplest triangles
yeah.
I've ever written.
Just SOHCAHTOA? Cool. Cool, 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 cool. Great. Thanks. All right. So we've got some basics, right? There's some things that we might come up, some terminology, but these are kind of the basics, right? We're gonna have an initial side, a terminal side. It's gonna be positive or it's gonna be negative, right? And things being coterminal just mean that they end at the same point. Okay? So in many applications, here we go, radians. So in many applications, we will prefer to measure angles in radians. Okay? So in many applications, we will prefer to measure angles in radians. So what is a radian, you ask? Radians. If you have a circle, circles, right? So if you have a circle with a radius r, then the measure of the angle in radians, okay, so we've got a circle here. Maybe if I hold it, haha. Technology, right? Cool. All right, so we've got a circle, and maybe I'll even, can I move it? I want to be able to use the lines for the radius. We've got a circle with radius r. And actually, I'm going to put this, just because I'll have not enough space, I'll put this r down below. And let's just say that I've got another, so now I'm taking out a slice here. Of course, that's also going to have a length of r. It doesn't really factor in, right? But just keeping in mind that the radius is going to be the same everywhere, right? And so now we've got this section, right? And I'll kind of put it outside, but of course I mean the section on the circle. And we're just going to call this S. And maybe I'll use screen here. And then we've got some theta. How are you guys' Greek letters? Theta, good, top notch, nice. So theta, we use Greek letters for angles, typically lowercase, theta, alpha, beta, gamma, whatever. Right, and I'll kind of introduce them, but theta is pretty common, right? And so we could measure theta in degrees, right? But now we want to talk in radians. So what does a radian measure? Well, it measures the ratio between S and R, right? And so if we want to measure theta in radians, theta is going to be S over R. So it's the ratio, therefore, theta in radians is the ratio of the length of the arc that subtends the angle. Can we go there?
No.
It's just the length of that arc, right? So the length of the arc that, I'm going to do it anyways, subtends the angle. All right. But I'll clarify that that's S to the radius. To the radius R. Just connects those two lines that make theta, right? And so S subtends theta. Yeah. I guess you could think of, there's points here, right? I don't know, call it, yeah. Ten. We're doing it, guys. If we count the Zoom room, folks, I think I'm there at 50%. Feels good. Solid pass. Yeah. Yeah. Okay, so theta is just going to be, it is the angle, right? But instead of talking in degrees, we talk about the ratio of S to R, right? So S over R, and that's going to be your angle. So if we think about kind of a special case, right? So consider I'll do my homegrown circle. I'll let technology do its thing. We've still got a circle with a radius of R, right? And now what I want to do is I want to force this arc to also have a length of R. Right? So now I'm kind of taking it the other way, right? Because what's that going to do to our angle, right? If we end here, because that's the length R, well then at this point, we've got theta there. That angle has to be 1 radian, right? So 1 radian is, if you've got a radius, any radius R, right? And then the length of that arc is also R, then the angle has to be 1 radian. And so that's how radians kind of behave. Yeah? And so now we've got theta is R over R radians which is just going to say that theta is 1 radian. Okay. So, all right. What does that mean? I think if you've worked with radians before, right, 2 pi radians probably sounds a little bit familiar, right? But so let's talk about how many radians we would need to get around the whole circle, right? And so if this is 1 radian, then how many radians would we need to get all the way around? So let's use the fact that we know, right, that r is just a fraction of the circumference, right? And we know the formula for the circumference. And so we know the circumference of a circle is c equals 2 pi r. So now, if I draw another circle here, same deal though, radius r, and now I've got this angle that's going all the way around. Counterclockwise, why not? So now I'm saying, okay, well, I guess I've been using this color. This length all the way around is 2 pi r. If this orange one is theta, we can use that same method and say that, well, theta is s over r, right? S is the arc that subtends the angle, and so s in this case is 2 pi r. So we've got 2 pi r over, the radius is still just r, radians. Right. And so those r's are going to cancel, and so we have just theta is 2 pi radians. So a complete revolution, right, or a complete, I'm trying to not say 360 degrees, right, but that's what it is, right? So a complete circle is going to be 2 pi radians, right? And so now we can break up, instead of 180 degrees, right, that's going to be pi radians, and then we can break it up into fractions of 2 pi. We know the angle of a full revolution, in degrees is 360 degrees. So we can now develop conversions. So we said, okay, in radians, a full revolution is 2 pi radians, right? So we'll start there with 2 pi radians is equivalent to 360 degrees. So then, if I want to move from a radian into degrees, right, then I can divide both sides by 2 pi and just be left with 1 radian on the left-hand side, and then whatever 1 radian is worth in degrees on the right-hand side. Right? And so we can have 1 radian is 360 degrees divided by 2 pi. We can simplify that a little bit, right? We can divide 360 by 2 to cancel that 2 in the bottom. 1 radian is 180 degrees divided by pi. So now if you have something in radians, then you can convert it to degrees, right? And vice versa if we take it the other way. Or solving for degrees, starting at the same point, we have 2 pi radians is 360 degrees. But if I just want degrees on the right-hand side, I move everything else to the left-hand side, and so I get 2 pi radians over 360 is 1 degree. Oh. But again, I can cancel that 2 into the 360, and so I get pi radians over 180 is 1 degree. Put a little box around here. Right. Just in case you need to convert from radians to degrees or vice versa. All right. Okay. Any questions so far? No? All right. So let's just establish 3 facts. 2 positive angles, 2 positive angles, alpha and beta, right? And it's only true for positive angles, right? Meaning they're moving in the counterclockwise direction. 2 positive angles, alpha and beta, are supplementary if alpha plus beta equals pi. Thinking about, right, a circle, with some radius r, right, some midpoint, well, this length here, or that angle, sorry, is pi, right? Pi radians. So basically, if alpha plus beta equals 180 degrees, right, we're used to talking that way, but now we're going to talk in terms of radians, right? So if alpha plus beta equals pi, then they're supplementary. Same idea, they're going to be complementary. And this is the same terminology as we had for degrees, right? It's just with radians. So they're complementary if alpha plus beta equals pi over 2, right? Which is essentially 90 degrees. guess I could draw that out too. Pi over 2. And finally, kind of the moneymaker is their coterminal. Their coterminal, if, let's talk in terms of beta, if beta is, now let's think about this, right? So coterminal means that, okay, we've got some angle and we want to end up at the same terminal, right? And so if we've got circle with a radius r, right, and we've got, let's just do kind of this basic one. We've got this angle alpha, and now beta has to end up at the same terminal angle, right? So it has to have the same terminal side. Well, one option, or let's use a different color. One option is for beta to just go alpha and then another circle, right? But you have to go to alpha and then you have to go another circle, right? Or you can do another circle and another circle, and another circle. They're all going to be coterminal, right? And so, and then remember the angle of a full circle is 2 pi, right? And so here, if we have to go like this, and this is beta, right? They're coterminal. And we could just keep looping, 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 or we could go backwards, right? We could start at alpha and we could go backwards 2 pi, right? It would be the same thing, right? But you'd have to start at alpha and then loop back. But each revolution, a full revolution, is still just 2 pi. And so we have to start at alpha. So beta has to be alpha. And then we have to add plus 2 pi, that's one revolution, and then times k for some integer k. We could even say any integer, right? An integer is a whole number, right? It can be positive, it can be negative, right? But it has to be a whole number. And so that's exactly what we're doing here in this equation is we're saying, okay, well, beta, we have to start at alpha because we have to, that's where we have to end up. And then we're just going to do full revolutions, either clockwise or counterclockwise, all right? And so that's how we're going to find coterminal angles. Right? Better put a box around this. Especially that coterminal one, we're going to use that. Dun, 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 dun. Oy. So one thing that's kind of nice and weird about radians is that they're unitless. So although we say 2 pi radians, right? The angle is actually just 2 pi, right? And so, and even though we might say pi over 2, the angle is, and then we tack on radians, but that's just because we like units, right? But what's nice about radians is that it's actually unitless, right? And so if you're thinking about dealing with units and canceling units and kind of figuring units out, the fact that your angles don't have any units right? That's going to be nice to deal with. So although we say 2 pi radians, for example, radians are actually unitless. Unitless? Unitless? I feel like it's weird if you smush them together. I don't know. Lacking units. So just keep that in mind. So it's fine because we usually do say radians, right? But if you're dealing with units, right, then you can just ignore the units for the angles. All right. Example 1. Graph each angle in standard position. I'll just put in brackets here. Standard position is initial side on the positive x-axis, which is probably, that's where I've been starting all my radii anyways, right? So I just kind of always start on the positive x-axis, and I think that's what you would default to as well, but that's called the standard position. So the initial side on the positive x-axis so graph each angle in standard position, classify each angle according to the quadrant in which the terminal side lies. According to the quadrant in which the terminal side lies. Right. Keeping in mind that you've got your XY plane here. This is quadrant 1, 2, 3, and 4. So yeah, so if you just say, so context, right? Like if you're talking about an angle and you say that it's pi over 4, for example, then you, like usually in speech we say radians, and even writing it down, because we don't like to just say, oh, that angle is this, right? Because we like to have units. So even if you write out radians, it's fine. But then, yeah. We'll do an example. Okay. Yeah. Okay, so depending on where your terminal side is, right, you're going to classify it as a quadrant 1, 2, 3, 4 angle. And then we're going to find 3 coterminal angles. At least one of which is positive and one of which is negative, right? Whichever one you find. So find 3 coterminal angles at least one of which is positive and one of which is negative. Okay. So, you ready? We'll start with alpha is pi over 6. So alpha is your angle, and it's pi over 6 radians. Yeah. All right. So first, we're going to draw this, right? So pi over 6, you could imagine where it's going to be, right? Because you know that a full revolution is 2 pi, and so you could kind of pick your way to pi over 6. Or if you think about it as, okay, well, pi over 6 is some portion of 2 pi, right? And then we can figure out what portion of 2 pi it is, and that'll be easier to map out. Okay. So what I mean is that we find pi over 6 is a portion of 2 pi, right? A full revolution. So what we're going to do is we're going to do pi over 6 and then divide it by 2 pi. We've got a fraction over, technically a fraction, right? If you imagine it's 2 pi over 1. So this becomes pi over 6 times, now flip and multiply, right? 1 over 2 pi. Now, all of a sudden, sorry, I didn't know if it was a question hand or a stretch hand, so I had to wait it out. Just a stretch hand. So now, all of a sudden, these pi's are canceling, right? So we don't have to deal with pi a lot of the time, but you do have to keep it as just pi. Pi is a constant, right? And so you can just treat it as a constant. So now you have 1 over 6 times 2, which is 1 over 12. So therefore, alpha equals pi over 6 is 1/12 of a revolution. Now, if you do 1 over 12 on your calculator, I get 0.833. So it's 8% of a revolution, right? So I know at the, sorry to keep bringing up degrees, salt in the wound, right? 90-degree mark, right? I'm at the quarter waypoint, so 25%. So I know I'm in that first quadrant, right? And so we don't have to be very much more specific than that, right? We know that our angle is pretty small, right? Because it's only taken us a 1/12 of the way around, right? So you can split up your whole circle into 12s, and it's just one slice of that, right? Or because we're just approximating here, oh, that was a weird line. So now I've got my initial side on the positive x-axis. And then I've got
12. 12 would be 180, or that'd be 360.
so if you've got 12 twelfths of a revolution, that's a full revolution, so that would be 360 or 2 pi radians, or 360 degrees or 2 pi radians, right? But now I'm just breaking it, the circle up into a fraction.
Can you not know, if you know that a full revolution is 2 pi radians,
Mm-hmm.
and assume that every 90 degrees you go pi over 5. Pi over 5.
Pi over
90 degrees and 180 degrees would be 1 pi.
pi over 2?
No, like, because we have pi over 6, and we know
Yeah.
that, we know that 2 pi is equal to 360 degrees.
Yeah.
Can we not say, okay, at 90 degrees then it's pi over 5? Then
Yeah, if you like pi. Which, yeah, I know, right? No, that's great, right? I'm just trying to show you a way that you can ditch the pi, right? Because pi can be kind of weird to deal with, right? And so, but definitely that is what we're doing, right? We can say, okay, well, here at this point, I'm at pi over 2. Here I'm at pi. Here I'm at 3 pi over 2. Here I'm at 2 pi, right? And so you can definitely just do that. It'll be quicker, easier, eventually. But I'm just showing you a way to get rid of the pi's so you can only deal with numbers that we like. 1/12 of a revolution, or less than pi over 2. Nice. So here, this is probably too big of an angle, but alpha equals pi over 6. Just sketching it out. As long as my angle is kind of reasonably in the first quadrant, right, then I'm not too picky. So alpha is a quadrant 1, oops, quadrant 1 angle. Oh. Here's the part that I actually care about, finding those coterminal angles. So now, to find coterminal angles, we can use beta or theta or whatever. We use, I've got theta in my notes here. Better do that, otherwise I'll trip up. Theta is alpha plus 2 pi times k for any integer k. So what we can do is, okay, well, I know what alpha is, right? Terminal angles, I'll just throw in that, I'll call them theta. We use alpha plus 2 pi times k. So what I'm gonna do is I'm just gonna pick 3 different values of k, and remembering that I want at least one positive angle and one negative angle, and another one can be whatever it wants, right? And so I'm gonna play around with different values of k to see where it gets me. And so if I let k be, well, let's go 1 revolution, right? If you think about k, how many revolutions you've done, right? Let k be 1 revolution, then you get theta is alpha plus 2 pi over k, or 2 pi k, sorry, over k. alpha is pi over 6 plus 2 pi times 1. So then, in order to add these, right, and simplify these, we have to have a common denominator. And so, and we've done a lot of that. So pi over 6 plus 2 pi, and I want them both over 6, so I'm going to multiply this guy by 6 over 6. There's lots of kind of clever ways that you could do it, right? You could have started and rewrote 2 pi as something over 6, but, right, 12 pi over 6 is 2 pi. But I like this approach. It gets you to the same thing anyways, but it just shows that, okay, I'm just getting a common denominator. So now I've got pi plus 12 pi all over 6. So theta must be 13 pi over 6. So pi over 6 and 13 pi over 6 are going to end up at the same point, right? So the coterminal. What if we let k be -1, right? I'm just picking, you could have picked, bless you, you could have picked -13 if you wanted, right? You can pick any value of k as long as it's a whole number. And so, but I'm just going for the easy ones. So my go-tos are going to be 1 and then bounce to -1 in order to try to get that negative value, right? Because I have to get a negative value. This gave me a positive, right? And so now I'm going to try a negative k, but I'm going to stick to 1, right? Just 1 revolution backwards. And then I'll bounce to 2, how about, right? That's right, yeah. So if we let k be -1, then we've got theta is pi over 6 plus 2 pi times -1. So now it's gone to pi over 6 and then it's going backwards to pi, right? But it's still going to end at the same point. So again, pi over 6 minus 2 pi times 6 over 6, just to get that common denominator. So pi must be, or sorry, theta must be pi over 6 minus 12 pi over 6. So theta must be -11 pi over 6. So now we have that negative angle, right, going clockwise. Because if you visualize it, right, then if we start here, right, our initial side for both these angles will be the standard position, right, on the positive x-axis.
You always go from your terminal, though, don't you?
Well, you always start, so both these angles start on this initial side.
But like when you're
Right.
doing the negative, you have to, because you're doing essentially, you're doing the pi minus, or the 12 pi minus the 1 pi, you have to go from the terminal.
Yeah, but, oh, but then, so we've got theta and then we start at alpha, right? And so theta has already been moved from the initial side. So from here, it's moved to alpha, right? If we go to this equation here, right? Theta is the angle, the new angle, right? So it has to start at alpha. So it has to start here, for example, right? But it starts at the same initial side as the other angle, right? And then, so that's why we've got that alpha jumping off point. And then we go revolutions around from there. Right? but they'll have the same initial side. And so if we've got, let's say, this angle here, then actually, I'll just do the one that we just did, actually. Here. If this was pi over 6, right, then if we move from here, negative 11 pi over 6, that's going to get us to the same point. Right. Should clean up that. That's right. And then what does 13, was it 13 pi over 6? Yeah, 13 pi over 6 was, okay, so we start at the same initial side, running out of colors here, green. If we start here, then we went all the way around 13 pi over 6. Right. And then one more. Oh, nice. All right. Sure looks like it, doesn't it? I am confident, actually, that for any sort of, so for motion, radians are kind of the, like, so kind of cyclical motion, right? Radians are the measure of choice. Right? And so, right, even waves, currents, right, anything kind of cyclical will likely just be in radians. Yes.
To be able to show it like the 5 or 6, all right, it's going to be 13 5 or 12.
I want to see the work. It's not that bad. But it's only because if you're doing like 13 revolutions or something weird like that, right? Like with these, it's easy enough to kind of visualize, but it's good to kind of have that work behind you, right? Even if it's obvious sometimes, right? So I want to see it. No, because the maximum angle, right, is going to be 2 pi, right? So you're never going to exceed 2 pi. And so what happens is they just kind of like cancel out, right? So I think that's what you said, right? That they would cancel. Well, 13 over 6. 2. Oh yeah, so then we would have to simplify it. But 13 pi over 6. Oh, I guess we're just indicating how far we've gone. And then we can simplify it to pi over 6. You can have more than 2 pi. But the angle wouldn't be more than 2 pi. Like the angle from the initial side wouldn't be more than 2 pi. But the overall, because it's taking into account the revolutions as well. Let's see, with k equals 2, it's going to be more than 4 pi, I think. Let k equal 2. Theta is alpha plus 2 pi k. Theta is pi over 6 plus 2 pi times 2. I'm going to throw in times 6 over 6 to simplify. Right, get that common denominator right away. So I get pi over 6 plus 2 times 2 times 6 is 4 times 6, 24 pi over 6. So then theta is 25 pi over 6. You look like you're regretting getting out of bed. It's good. I'll give you another angle. How about? This time beta, negative 4 pi over 3. First sketch it out. Figure out what quadrant the terminal side is in, and then find 3 coterminal angles.
This means it's coterminal. Because it would be equal something.
Oh, I'm just using beta as the name of the angle now. So now, if you're going for the coterminal, if you call it theta again, you don't have to, but call it theta, would be beta plus 2 pi k. Theta is coterminal to beta. So you can have any value in there or any angle in there. I'm calling it beta.
That's just a variable.
Yeah.
How do we know?
Any Greek letter is going to be an angle, a variable for an angle.
How do we know when it's going to be something that's complementary?
Oh yeah, but if any 2 angles, regardless of what they're called, right, any 2 positive angles that add to pi, for example, right, they'll be, is it complementary or supplementary? Yeah. And then pi over 2. So those alpha and beta in there, we can interchange with whatever we need. Yeah.
Just a memory question
Yes?
and a stretch. Okay, so we have negative 4 pi over 3. The over 3 would be equivalent to pi over 2, right? Correct? So 3 would be 90 degrees. If you were negative 4, or if you were like negative 6 pi over 3, then you would be 180 degrees.
Yes. Wait, negative 6 pi over 3 is 2 pi. Right, so then you've gone backwards to 2 pi.
No, you're right.
Right? But I think your idea is
But like the
good,
over,
right? Because you can look at, okay, so a
over,
third.
Like over 3 is the same as saying pi. That would be 1 pi.
Over 3
Yeah.
is you have your 180 degrees divided into 3 parts. So it takes 3 parts and then another third below. That's how I see that.
Yeah. So I think, yeah, we're all gonna have these kind of ways of getting there, right? And so the way I showed you is, okay, so you can simplify -4π/3 into just a fraction of the circle. You guys didn't seem to like that. And so maybe if we think about, okay, well, if it's over 3, a full revolution would have to be 6π/3, right? 6π/3 is 2π, right? You can think about it that way. And so 4π/3 is, well, 4π/3, I don't know. Let's see. So if we break up our circle, remembering that we're moving backwards, right? So we've got our kind of initial side, okay? And then I'm just gonna break up. So from here to here, actually, let's start with the full way. This would have to be 6π/3, right? And it's negative, but only because we're moving clockwise, right? So we can kind of ignore that negative.
I'm sorry, why is it less than?
Oh, because I'm just showing a full revolution, kind of
Oh, because
nitpicking,
that
like
would go
taking,
into
right?
that.
Because 6π/3 is -2π, right? 6/3 is 2. And so if I've got a 3 in the bottom and I need that to cancel and to make 2 on the top, right? 2π, because then I know what a full revolution looks like, right? And so a full revolution is going to be 6π/3. And so, but I've only got 4π/3, right? And so what I'm going to do is I'm going to kind of break this up even more, right? And so if I'm here, let's say, so if I'm starting here, oh, and I only go this way, right? Then I've got what? I've got -3π/3. -3π/3 is just pi.
It's like 4 quadrants. So if it's over 3, would it have 3 sections in the circle? Yeah. Like Rich said.
Say that again.
Since it's over 3, would there be 3 sections in that circle, and you kind of made it into quadrants?
Oh, yeah, because I'm used to, so the reason I made it into quadrants is because I know that from here, well, I've got π/2, I've got pi, I've got 3π/2, and then I've got 2π, right? So I'm sectioning it into quadrants because I know how it behaves at those checking points. But what you could do, right, π/3, halfway here, like Richard was saying, right? We're gonna land on that, I think, right? You could say, okay, well, here up to this point, right, I need to have pi. So if pi is over 3, then I've got 1π/3, 2π/3. Oh, sorry, I'm bad at sectioning. π/3, 2π/3, 3π/3, which is the same here, right? Okay. Let's draw that instead. Or starting here, and we know that here, up to this point, we need 3π/3. Not really writing it as an angle, but I'm ignoring that for a little bit. So now if I have to split this top half of the circle into 3s, right, because by the end of it, I want a full pi. And so now I can split this into 3 sections. So this angle is π/3. This angle is worth π/3, but not, the initial side is changing, right? So they're not connected. This side is pi over 3. And this side, and this side. So if I need 4 pi over 3, moving backwards, right, then now I can just start and say, okay, well, 1, 2, 3, 4, that puts me here. And so how do I make room? I should have made a bigger circle. Four pi over 3 and negative because we're moving clockwise. Hard to draw. As long as you got there, like I'm saying, there's lots of ways that you can kind of slice it and dice it in your mind. Right? This seems to be the preferred method, and that's great. As long as you have a way that you like and you kind of feel comfortable with it, then that's great. Okay. And so, yeah, so if you've got something over 3, then you can just divide each half into 3 and go from there. Yeah. I'm afraid to ask if there's any questions. No. So, sorry. Total.
By the time of the circle, you have to have two pies.
Yeah. Yeah, so whatever's in the bottom, I guess, right? And then you take kind of your top half or your bottom half, whichever one you prefer, of your circle, and split it into that many sections, and then replicate it in the other part, right? Just flip the, just do it, guys. I don't know what the problem is. No, I do. It's hard. Yeah. No. And yeah. But we'll keep working on it. It's a lot. Well, and because it's so weird to us, right? We're used to degrees. We're comfortable with degrees. So why would we use radians? Well, there's, yeah, exactly. Oh yeah, totally, right? Yeah. Yeah. Mm-hmm. Yeah. 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 Right? So beta is what quadrant? Quadrant or 2? Yeah, because it's negative. Beta is a quadrant 2 angle. There's a lot. Yeah. All right. Let's find some coterminal angles. But coterminal angles, you're just going to use the formula, right? And so that's not too bad, right? And so we know theta is beta plus 2 pi k. And so if I let k be my go-to 1, you can pick whatever you want, but I'm going to stick with my usual 1, -1, trying to get a positive and a negative angle. And then, I don't know, up it to 2. Go crazy. 20. No, too many. Like KB 1, so then theta is beta, which is negative 4 pi over 3. Oops. Negative 4 pi over 3 plus 2 pi times 1. Theta is negative 4 pi over 3 plus 2 pi times 3 over 3. Oops. So theta is negative 4 pi plus 6 pi all over 3. So theta is 2 pi over 3. So now we've got a positive angle. I'm trying to get that negative angle, so I'm going to let K be negative 1. So theta is beta plus, actually, I'm just going to go right to it. Negative 4 pi over 3 plus 2 pi times negative 1. And then I'm just going to get that common denominator right away. Ugh. Negative 4 pi minus, right, because I've got that negative 1 times 2 times 3, so minus 6 pi, and that's all over 3. So I get theta must be negative 10 pi over 3. And we need 3, so let's just do a third one. Right, let K be. So you're 5. No way. I'm gonna do 2. Are you crazy? You'll finish that page yet, huh? Negative 4 pi over 3. It's the soothing sound of my voice that's helping you read.
It is. It really is.
Just droning on and on and on.
And just
Oh, yeah. Well, it's better than, because my afternoon class is in that room, and I guess this class just watches movies the whole time, and they have the volume up so loud. It's, yeah, it's crazy. But I'm also kind of like, what class is that, and how do I teach it?
Student math 101.
Yeah, they're like, get out. Yeah.
yeah, that's basically what it would be.
2 times 2 is 4 times 3 is 12, so plus 12 pi, and that's all over 3. Negative 4 plus 12 is 8 pi over 3. Okay. Any questions about those?
So those are all equal.
Yeah.
It doesn't matter what K is.
Well, K has to be a whole number, but they'll all end up at the same spot, right? Let's talk some circular motion. Stepping on the toes of physics here. Suppose an object is moving along a circular path. Earth, for example. Wow, what an example. Right, with some radius r, and it moves from a point P to a point Q, right? Just establishing sort of some points here. Suppose an object is moving along a circular path of radius r from point P and Q, point P to Q, I'm going to say, in an amount of time t. So what that's going to look like, if we sketch it out, is we've got a circle here, and we've got a radius r. We can draw these lines extending out. And we said that this point is point P, and this point is point Q. And this angle here, we're going to call it theta. Let's talk about this distance, right? The distance between P and Q, if we're moving on the circle, right? That's going to be the displacement, right? And so if this here, S, let's call it, just like we did before, the distance, shouldn't really say distance, but just for argument's sake, the distance between P and Q, put quotes around distance. Distance is a little bit different. Is the displacement, and we denote it by S. Well, because technically the distance between P and Q, well, those will be coordinates, right? And so we could find the distance between those coordinates. But I want you to kind of imagine, right, that the track between P and Q, right, that's the displacement. But I think you guys have probably talked about displacement in physics, right? So it's just how far you've gone. That's why I'm a little bit hung up on the distance, but in terms of kind of thinking about it, right, it's the track, the amount of ground we've covered, right? Okay. Is there a fancy T going on?
Well, I was drawing up this T, right?
Right, as you do.
Yeah.
Yeah.
And at the bottom is a little flare.
Mhm.
Like, here, it's an anchor.
Nice.
Fun fact.
Cool.
Yeah.
Really cool. Fun fact.
That's what I'm thinking in this class.
Isn't it more of a like a fish hook?
Well, it depends how much you flare it. Like,
Oh,
yeah,
it's all in the wrist.
exactly. Yeah.
Okay. So S, right? Now we're going to adopt that same kind of method, right? If the displacement is counterclockwise, it's going to be positive, and if it's clockwise, it's going to be negative. If the displacement S is counterclockwise, S is greater than 0, and if the displacement S is clockwise, S will be less than 0. Let's get some other fun facts out of the way here. V bar, remember anything with a bar over it is an average, right? It's the mean of something. And so V bar is the average velocity. Oops. Which is also, or actually, the average rate of change of the position of the object with respect to time, right? And so average rate of change, I don't know, that sounds familiar, right? We've talked about average rate of change. And so the velocity is the average rate of change of the position of the object with respect to time. The absolute value of the average velocity is just the speed. So is the speed of the object right? Because the average velocity can be positive or negative. We can write that V bar is displacement over time. Which we can shorthand as S over T. Now we've seen S before, right? S was part of the definition of a radian, right? It was the arc that subtends the angle, right? And that's how it's behaving here as well. So we know if we are measuring theta in radians, theta is S over R, right? So solving for S, right, we can just multiply both sides by R. So S must be R times theta. which means that you can measure or find the displacement by taking the radius, assuming that you know the radius and the angle, right? You can multiply the two to get the displacement. And so what we said that v bar, the average velocity, is s over t, but s we can replace with r theta over t. And I'm just going to rewrite this as v bar is r times theta over t, only because theta over t is the average angular velocity. Average angular velocity of the object. And it's denoted by omega bar, lowercase omega. Oh, that was a bad omega. All right. My W's and omegas look a lot alike, unfortunately. But I try to make them kind of more, my omega, I try to make it more kind of bulbous. I don't know. It's hard. You guys seen omega before? No. Some? Oh. It's lowercase omega. Okay. So what we've got, right, is we've got this object moving on a path with some velocity, right, some angular velocity on the circle, right? So we're moving around with an angular velocity. And so what happens is we can actually straighten out that, that path and make a straight line. And then we've got a linear velocity, which we can also calculate. So if the path of the object were straightened from the circle, then the velocity of the object on that line segment would be the same as the velocity on the circle. For this reason, right, so now we had an arced velocity, an angular velocity, and now we're straightening it out, and now we've got a linear velocity, right? So for this reason, v is often called the linear velocity of the object to distinguish it from the angular velocity omega. to distinguish it from the angular velocity, omega. So these two are, of course, related. So if we want to talk about the velocity of circular motion, it's kind of a definition, I guess. For an object moving on a circular path, of radius r, with constant angular velocity, omega, omegas give me grief. The linear velocity, I'll put linear in brackets, the linear velocity of the object is given by v is the radius times the angular velocity, omega. Which means that you can move between the two, right? The angular velocity or the linear velocity, as long as you know the radius that you're dealing with, right? Then you can move between the two. A little. Any questions about that? Example 2. This is one of those ones I should have typed out. And maybe, just maybe, we should use it for review next day. How do we feel about it? Everyone's pretty good with that.
I agree.
Then I can type it up.
Yeah.
How about?
Yeah.
Because it's really long. All right.
Then we're gonna forget about the weekend.
Yeah, it's best, right? I am spending my long weekend marking in Ottawa. Yes, I am. Well, I mean, yeah, it's not your fault. I know, right? But it's just so you can be jealous. At least it's not outside in Ottawa.
Worst case scenario.
Yeah, it should be pretty good.